Hello, I'm Lena, HMS Virtual Assistant. Today I will briefly explain how our power estimation algorithm for VRF systems works. To do so, we will use our configuration tool, Intesis MAPS. For real data collection, we've connected a Samsung VRF system consisting of 3 indoor units and 1 outdoor unit. Additionally, a pulse meter has been connected to the outdoor unit. And by using the power estimation algorithm, we'll demonstrate how the gateway can estimate the consumption of each indoor unit, even when they have different energy demands and user settings. We'll begin by creating a Modbus project for the Samsung VRF system. We connect the gateway by selecting the communication port on the computer, in this case, port 16. Then, from the Configuration tab, we set a valid password to protect the project. This step is mandatory when using maps. In this real-world example, we can perform a scan of the VRF bus to discover the available signals for indoor and outdoor units. Once the scanning process is complete, we can activate the power consumption option. We need to specify the type of meter that will be used to measure the total consumption. In our example, we're using a pulse meter connected to the gateway's binary inputs. Modbus TCP meters are also supported. We start by defining the meter's configuration parameters based on the specifications provided by its manufacturer, although users can modify these parameters if needed. For consumption estimation, we set our preferences, which can include general consumption or separate figures for cooling and heating modes. And for power unit measurement, we have chosen watts. We have enabled the option to overwrite and erase historical data so that we can observe the actual consumption starting from the moment when the simulation begins. Once the project is configured, it is saved and sent to the gateway. As simple as that. To demonstrate how the consumption estimation works, we'll go to the Diagnostics tab, where we can send data to the indoor units like the control system would do while monitoring the consumption variables. First, we verify there are no communication errors. Since we are directly connected to the VRF bus, just refreshing the signals will allow us to observe the real-time data. Initially, we see that the first indoor unit is off with its consumption objects, current, total, and accumulated, all in 0. The second indoor unit is also off, and its consumption objects are 0 as expected. The same applies to the third indoor unit. Let's select any indoor unit, for example, Unit 3, and change its status by sending a 1, which powers it on. The fan speed is automatically set, but we adjust the set point temperature to 24 degrees. Initially, the communication objects are still 0, but remember that it takes a moment to refresh the data from the bus. We also want to let the unit run for a while under these parameters so that new consumption data can be recorded. Once updated, we see the consumption value has changed to 8 watt-hours. The total remains the same since there are no historical data from previous days. Let's now select another unit while Unit 3 continues to register additional data, which now shows 16 watt-hours. We turn on Indoor Unit 1, update its set point to 25 degrees, and ensure it is operating in heating mode, where energy consumption is typically higher. After a moment, the data refreshes again. Continuing to monitor the values, Unit 2 remains off, Unit 1 updates to 10 watt-hours, and Unit 3 reaches 27 watt-hours. In conclusion, we have demonstrated how connecting this gateway to the outdoor unit and using a single energy meter allows for a reliable power consumption estimation. This algorithm meets the criteria established by OEMs and takes into account the usage parameters and energy demand of each indoor unit, enabling independent consumption identification for each unit. I hope you found this information useful, and thank you for your attention.